Hi guys, Mrs. Rona here. I'm going to talk you through linearization notes. So let's look back at the Speedier Lab in the 2018-2019 packet. This is on page 14. So take a look back at the Speedier Lab and look and see, are all the graphs straight lines? Hopefully you see that the velocity time graph is linear, but the position time graph is not linear. And we talked in our board meetings that we can't get a physics equation if it's not a straight line. Well, today what we're going to do is fix that issue. We're going to be able to get physics equations even if our data is not a straight line. What we have to do first is make it into a straight line to use y equals mx plus b. And this is a process called linearization. It's not the same thing as just putting a straight line on your data and doing line of best fit. We're actually going to manipulate the individual data points so that we can get an equation. What I want you to do now is turn to the front of your packet and find the part that shows different graph types. In the 2018-2019 packet, this is on page 3. So turn your packet to page 3, and hopefully what you see are these 3 along with 2 others. So we have different graph types. We've got a horizontal graph shown here. We've got a linear graph. We've been working a lot with those. We're happy with those. We've got an inverse graph. I want you to know that there's no x or y intercept on this inverse graph. That's a new relationship we haven't looked at. We also have a quadratic. We've looked at that one, seen that before, and haven't done much with it quite yet. And then a square root, which is, I like to call it a quadratic turned on its side. So those are the 5 graphs you're going to be responsible for knowing. So let's talk about what we can do with those to still make them linear, so going back to that straight line fit. I want you to note that none of these were exponential. AP readers said that many students are using the words linear and exponential too often. Linear is fine if it's linear, but exponential is just too broad of a word. So we are not going to use the word exponential anymore. It's going to be considered a physics curse word. So I want you to use, if you think it's a quadratic, use the word quadratic. If you think it's a square root, use the word square root. So no more exponential. All right, so if we want to write a linear fit or a linear equation for these lines, do we need to change these graphs at all? No, we don't. These are already linear, right? This would be something like y equals 3. We could do y equals mx plus b for this line. No need to change your data for these. For these, can we use y equals mx plus b? That would not work. We would need to modify these graphs somehow in order to write our linear equation. So are modifications required for these? Yes, absolutely. And I'm going to teach you how to do that today. So here, what you would do for this one, and I would suggest following along on page 3 for this, you want to look at the graph, and in order to make this linear, we would graph y versus 1 over x. We would take the inverse of every single x data point. In order to make this one linear, we would graph y versus x squared. If I took every single data point and took the x value, if I square them, my graph would turn into a straight line. For this one, the square root function, we would square the y value. So taking every single y value in your data set and squaring it. You could also take the square root of the x. I will talk about squaring the y, but what I just mentioned would also work. So the question becomes, if I linearize a data set, can I still use y equals mx plus b? The answer is no, not really. We have to modify our y equals mx plus b. So if we have a linear fit, we've got y and x, we can use y equals mx plus b. However, if we have to take the inverse, if it's an inverse and I take an inverse of all the x values, then I need to put that in the equation as well. So I'm going to do y equals m 1 over x plus b. Whatever I did to my data set, I need to put it in my equation. If it's a quadratic and I square all the x's, I need to square the x's in the equation. If it's a square root and I square all the y's, I need to put the y squared in the equation. Students mess this up and the units way too much, okay? Don't be that student. When we do a linearization, reflect that in your equation as well. All right, so now I want you to look at page 38 in your 2018-2019 packet, It says Intro Linearization, I believe. So turn to page 38. And what we're going to do is we are going to linearize data here so that we can easily fit a line to the data and then use that equation to make predictions. That's the whole purpose of linearization. So we're going to practice with just writing physics equations for some data that's already linearized, and then I'll model how to linearize it by itself. So looking at page 38, you're given a velocity time graph, and we want to determine what kind of relationship is this. So looking at page 3, how would you describe this relationship? I would describe it as quadratic, so write that one down. When it's quadratic, what needs to be done to linearize your data? You need to square whatever's on your x-axis, so in this case, I need to square the time. So if I square the time, I need to relabel my axes over here. So once it becomes linear, and you're going to have to trust me right now that when I square every single one of these time values, I get this graph. I'll show you how to do that in your iPad in a second, but first, square all the time values. What you're going to get is a velocity still on your y-axis. We didn't mess with that. But now your x-axis becomes time squared. Since we squared the time, we also need to square the units, so it's seconds squared. So now we want to fill in the units for the y-intercept and the slope. So if the y-intercept's -3, it's going to have units of meters per second, right? The same units that match my y-axis. Slope units are going to be rise units divided by run. So meters per second divided by seconds squared is meters per second cubed. If you don't believe me, write out the fraction, but it's meters over seconds times 1 over seconds squared, so you get meters per second cubed. Right now, you're probably like, what does that even mean? Don't worry about that. I want to know that you know the process. The process is changing your axes to make it linear and then reflecting that here. So now that this is linear, I can rewrite a physics equation using y equals mx plus b. So what that would look like for this one, it would be v, because that's what's on my y-axis, equals m, the slope with units, so 6 meters per second cubed, times x, what's on my x-axis, time squared. This is where people mess up a lot. They'll often put time in there, just a t, but because it's whatever's on your linear graph time squared, put that in there, minus the y-intercept, 3 meters per second. All right, try the next one on your own. Pause me really quick and try this next one. All right, hopefully you tried it. This relationship is a square root. When we have a square root, we need to square the y-axis, which in this case is velocity. Now we relabel our axes over here. So this becomes velocity squared. And we need to square all of the units. So squaring that would be meter squared divided by second squared. Not just like our acceleration units. We need to square the numerator and the denominator. Time is still in seconds. We didn't do anything to our x-axis. And now I need to put units here. The y-intercept units should match what I wrote here. So meter squared per second squared. The slope units are rise units divided by run. So meter squared per second squared divided by seconds is meter squared per second cubed. Again, if you don't believe me, write out the fraction. Just figure it out for yourself. Writing my linearized physics equation, I start with my y, v squared, equals the slope with the units, times x, which is t, plus the y-intercept with the units. This should be, yeah, no, that's right. Okay, let's try the last one. So pause me again, try this one. All right, so this is an inverse relationship. What do we need to do to linearize an inverse? We take 1 over all the x values. So here that's 1 over time. So relabeling our axes, we've got velocity in meters per second. I didn't touch that y-axis. My x-axis is going to become 1 over t, and the units become 1 over seconds. So whatever you do to your unit, make sure you also, or your variable, make sure you also do to your unit. Y-intercept units should match what you've got here, so meters per second. Slope units are going to be rise units over run units. So meters per second divided by 1 over seconds, that's a crazy fraction. I suggest writing that up. What you're left with is meters. So meters per second divided by 1 over seconds, the seconds cancel, you're left with meters. Writing your physics equation, you're left with v equals 8 meters, so the slope with the units, times whatever's on your x. So here it's 1 over t. We have to put that in our equation, plus the Y-intercept with the units. All right, so make sure you're good on this page, page 38. If you've got questions, ask your neighbor. But what we're going to do now is get out our iPads and we'll try number 1 on worksheet 7 together. There's going to be a separate video for that. Thank you for watching.